Hey physics fans, this is Major Sablon here, again from the nuclear side of the physics department. Today we're going to be looking at the energy from the nucleus. To get there, we have to understand what fission is. So consider the following. We have a reaction in which a neutron interacts with a U-235 nucleus. This interaction will produce what we call a fission event, where I have two fission fragments created and I have 2 to 3 neutrons. Notice the blue circle is a neutron. And, oh, by the way, there's this big yellow star event, which we're going to say is the release of energy involved in that fission event. This release of energy is critical for us because we want to tie that into what we can calculate using these equations below. So this energy, I can look at in terms of rest mass energy or disintegration energy. Really the difference between that is rest mass energy, it involves any amount of mass. If I were to convert it straight to energy, I can calculate that using this equation. Oh, by the way, we've seen this before, right? Einstein's famous E is equal to mc squared. It's on your RDC. Also on your RDC is the Q is equal to negative delta mc squared. Did you check your reading? It turns out this equation was not in your reading. Why do we give it to you then? You know what? It's important enough for us to give it to you because we care about the amount of energy due to the change in mass that occurs during a reaction like a fission event. Well, this disintegration energy, what we can do with it, again, it's that big star yellow event. We can use that energy in things like technology we have currently in the US. Take note of what I have here. Reactors, weapons. It's under the subheading criticality. So when we look at reactors and weapons, we are concerned about whether or not we can get them to sustain a chain reaction. In order to sustain a chain reaction, we have to achieve what's called critical. Critical implies that there is an amount of mass that is sufficient to sustain that chain reaction. In reactors, it turns out we can control it. In weapons, we want to achieve what's called supercritical, where it's an area where we cannot control that chain reaction. Those technologies are available to us, and we could use that here in the US. Weapons, we're not really going to touch that. But to look at your gun type and implosion types, if you want to learn more about it in NE 450 here in the paint department, you can, just not currently in this course. Moving on, we have this thing called enrichment. So enrichment, really what we're looking at is the upgrading of the fissile material of U-235 that is in the natural state of U-238, about 0.711%. We want to upgrade that to a percentage that is either low or high. Typically in reactors, we're looking at about 3 to 5%. If we're looking at anything higher than that, maybe above 20%, the International Atomic Energy Agency specifies that anything above 20% is considered special nuclear material. If we were to get to weapons grade type enrichment, we're looking at about 90% or higher. Anyway, in order for us to get there, to get our natural state of uranium, U-238, to siphon out the U-235 and then upgrade it some more, we use technology called isotope separation. Isotope separation comes in many forms. Historically, this is kind of what we've got, and we got some newer technology that's still developing. But all in all, we know that we can get U-235 fissile material from its 0.711% initial state to something higher to create and use for the technology available to us today. With that, that's the lesson. Thank you for joining, and I'll see you next time.